there was a discussion with department chair downstairs. Okay, so I think like okay. The important thing here is like as I said, prior is here is an argument like for frequentist statistics. Okay, some of their results can be considered as a special case, okay, of Bayesian model. Okay, so for every model, Bayesian or not, has some kind of prior in one way or another. Okay, here I mean, when we say like some kind of prior in one way or another, we are referring to certain assumptions. Okay, even if the prior is not set explicitly, I mean, we will have certain assumptions there. So many results from frequentist statistics, and it can be seen as a special case of Bayesian model under certain circumstances. With, for example, with a flat prior. Okay. For example, one of the important approach, okay, called maximum likelihood estimation, okay, which is proposed in traditional statistics. Okay, so this method avoids setting a prior and works just by finding a value of theta that maximizes the likelihood. Okay, so it doesn't have a prior, but it finds a value. Okay, the value of the of theta, which maximizes the likelihood. So you see, this is like one important difference between the traditional statistics and the Bayesian analysis, because in this traditional analysis, they came up with one value. But in Bayesian data analysis, we normally come up with distribution. Okay, so this value is usually noted by adding a little hat on top of symbols, something like this, theta hat. Okay, or we say it's a theta MLE, because MLE is an abbreviation of like maximum likelihood estimation. Okay, so theta hat is a point estimate. Okay, as I said, like this is a value, okay, and not a distribution. Okay, it's different from, I mean, the result, I mean, we obtain from the Bayesian analysis. So, okay, I mean, it's not like we cannot get that in the Bayesian data analysis. Okay, for example, for a coin flipping problem, okay, we can compute this analytically. So theta hat is actually y divided by n, the number of heads divided by the total number of trials. Okay, so if you go back to figure slide 101, you will able to check, okay, that the mode of the blue posterior, okay, to which is a uniform prior, okay, agree with the value of theta, okay, computed for each subplot. So this one. Okay, original is blue, right? Okay, so you can see when you have a one trial, one head, so the y divided by n is 1, right? Right? So you can see where you get the mode for the blue distribution. So 1, right? Okay, and okay, when you have two trials with one head, the y divided by n is 0.5, right? So for the uniform prior, okay, what you have, okay, is this one. This one you can see the max value, the mode, happen at 0.5, which is 1/2, right? And let me just, for example, okay, 4 trial, 1 head. So in this case, the theta hat, the estimated MLE will be 1/4, which is 0.25. I mean, you can see that, okay, for blue distribution, the max value happens somewhere here, which is 0.25. Okay, so basically, okay, the MLE, okay, the maximal likelihood estimate, okay, can be done, okay, you know, by the Bayesian analysis. I mean, you just need to assume you are using a flat plier, okay, and the MLE will happen at the mode of your distribution, okay? Okay. Okay. So okay, it basically like you know, MLE can be considered a special case of Bayesian model, one with a uniform prior. Okay. So there are a lot of like benefits, okay, of using priors. Okay. So we get several benefits. Okay. A distribution of plausible values, and not only the most probable one, because the prior is a distribution, right? I mean, you are not confined by just some possible values. You are actually able to provide like much more complete information for your prior knowledge to this problem, okay, because it's distribution as well. So also we get the transparent models, okay, meaning they are easier to criticize, debug, and hopefully improve, okay, because everything you know, can be seen, okay, from like the analysis. I mean, because you know, posterior is obtained from a prior and the likelihood. And the prior basically contains all the prior knowledge about this problem. So, you know, if you want to, you know, criticize or debug your model, okay, everything will be there. So it's very easy to observe, okay. And also, of course, like building models, okay, is an iterative process. We talked about that previously, right? Remember we explained what the model is, okay, and we explained like you know, how to build them, okay. So sometimes iteration take few minutes. Sometimes it could take years. So sometimes involve you, and sometimes involve people you do not even know, okay. So this is like you know, it depends. I mean, remember like we talk about. We didn't have talk about this, but we talk about like a lot of time like you are not the one to collect the data. Remember, I mean, when we talk about data collection, you know, I mean, so a lot of time, I mean, this data analysis is not done by only one person. It's actually a teamwork. Okay, so reproducibility matters, and transparent assumptions in a model contribute to it. This transparent assumption means that, I mean, you know, you pretty much wrap all the assumptions in your prior, okay? So we are free to use more than one prior, okay, for a given analysis if we are not sure about any special one. It's just like, you know, for different prior, we can have different result, okay? For example, just like what we have here, we have 3 different priors, right? So doing the analysis with different priors, I mean, it's never an issue, okay? It's, of course, I mean, eventually you need to see which one is the more plausible one, okay? So exploring the effect of different priors can also bring variable information to the table, okay? So it is actually encouraged to use different priors, I mean, in the analysis. So part of modeling process is about questioning assumptions. So prior, obviously, are just, your assumptions, okay? And different assumptions will lead to different models and probably different results, okay? So by using the data and our domain knowledge of the problem, we will be able to compare models, okay? If necessary, decide on a winner, okay? So when the chapter 5 in the textbook actually tells you how to do model comparison, okay? So of course, we will get to that point later, okay? So creating report and communicating results is central to the practice of statistics and data science, okay? So we will briefly discuss some of the peculiarities of this task when working with spatial models, okay? So we will keep looking at the example in the future, okay, about this important matter. So how do we communicate our analysis with other people, okay? How do we criticize the result, okay? So the first thing, okay, how do we represent the model, okay? If you want to communicate the results of analysis, you should also communicate model you use, okay? A common notation to succinctly represent probabilistic model is like this, okay? Theta, okay? This delta represent is distributed as, okay? So we know theta is distributed as beta distribution with alpha and beta to be the parameter, okay? Or you can say that beta is drawn from a beta distribution, okay, with alpha and beta being the parameter, okay? And then, okay, y is distributed as a binomial distribution, okay, binomial likelihood, you can say that, binomial likelihood, where n is 1, p is theta, okay? So this is just an example, okay? And there's actually visual representation of model, something like this. This is explained in the Kruskal textbook, the Doing Bayesian Data Analysis. Okay, so so obviously, like on the top, you can see the beta distribution. We specify alpha beta as parameter of this distribution. You may argue, well, the beta distribution does not necessarily look like that, right? It doesn't matter. Okay, it's just a we just we just put the beta here. Okay, here we just it's just we just represented distribution like that. Okay, with alpha beta parameters, and then okay, this delta represent the same meaning. So theta is distributed as that, and then this arrow represent that theta is sampled from the top distribution. Okay, theta is sampled from the top distribution. Okay, and then okay, which will be used in this binomial likelihood, right? This theta will be used in the binomial likelihood. Okay, and n is 1. Okay, it's another parameter, and then from this, distribution, you get your y number of heads, which is your data. Okay, so this is you can sort of think of this as like a visualized representation of this approach. Okay, this is a visualized. Which one is better? It's really up to you. But of course, like normally, okay, if you are a more visual person, then probably this is better. Okay, because sometimes like later on you will see that okay, it's normally easier to convert the visualized model into program. Okay, if I remember correctly, it's like converted from the bottom to the top. Okay, but anyway, like we will get to that point later. Okay, when we talk about next chapter. Okay. So on the first level, we have prior that generates the value of theta, then the likelihood, and on that last line of theta, y. So arrow indicate a relationship between variables, and the tail dot represent the stochastic nature of the variable. So that's about that figure. Okay. So the result of Bayesian analysis is posterior distribution. So this is very important. Okay. All the information about the parameters given a data set and the model is contained in the posterior, okay, posterior distribution. So by summarizing the posterior, we are summarizing the logical consequences of a model and the data, okay. So the practice is to report for each parameter the mean, okay, to have or model or mode or median, okay, to have an idea of the location of the distribution and some measure such as standard deviation, okay, to have an idea of the dispersion, okay, or the uncertainty of the estimate, okay. So you see, we need a way to describe the central tendency, where the central tendency is, and we need a way to describe how concentrate, okay, we are to that central tendency. So, I mean, we have described this repeatedly in today's class. Okay, the central tendency is normally represented by mean. The mu